Okay, so if we look at Maxwell's equations as we understand them, we can see that there's a real symmetry between the ones written in blue that involve electric fields, integrals of electric fields, and the ones written in green that are ones that involve magnetic fields. So if we look at this first Maxwell's equation, Gauss's law that we learned, we have this E dot dA is equal to the charge enclosed over epsilon naught. And then we sort of have an analogous magnetic uh, equation, which is B dot dA over some closed surface is equal to 0, but that's just a statement there that there were no magnetic monopoles. Okay, if there actually were indeed magnetic monopoles, I would actually write this as basically there would be some constant in front, mu naught. What the actual constant is not actually that important. But then it would be, times the sort of charge q sub b, sort of the magnetic charge enclosed, right? And since we live in a universe which, as far as we know, has no there are never any net magnetic charges that are separable, then basically this has to be 0, right? So basically, since there are no magnetic monopoles, this term is 0. But I could have sort of, for the sake of symmetry, written it in a very, very sort of analogous way to the electric fields, okay? And then for E dot dl, we just learned Faraday's law. So Faraday's law, originally we learned for static fields, this was 0, but then we learned that there was a correction if you have a time-varying magnetic field that will generate an electromotive force in a loop, right? And that was what we learned about last week. And then this is Ampere's law that we learned about. B dot dl is equal to mu naught I enclosed. And so, again, these two equations should look, should look quite analogous to one another, because again so this is a net electric current enclosed. There is no net, electric term, because basically there are no net magnetic charges, so we cannot generate a current of magnetic charges. If we could, there would be an additional term here, okay? But those particles, as far as we know, don't exist, so there is no additional term in this equation here that corresponds to this current term. However, in Faraday's law, we learned that there was this time-varying flux, so basically there was something that connected the time-varying magnetic flux to E dot dl. So that, begs the question of whether or not there should be some term here that relates the line integral of B dot dl to some time-varying, electric flux, right? Just in the same way that basically we have over here. And the answer is yes. So I'm going to just briefly go over an example that shows, how this is the case. This particular term that we write here is called the displacement current. It is not a real current, so it's not actually a real motion of charges. It has something to do with a time-varying electric field. So the name is a little bit unfortunate. I mean, you can imagine why people chose a name like the displacement current, because it acts kind of like a real physical current. But it is not an actual current of particles. Okay, so I'm going to just set up our example here. So let's imagine the following setup. So let's imagine we have a very long wire. Okay, maybe it's hooked up to a battery somewhere. We have basically a capacitor plates here that sort of interrupt the wire. Okay, so we have this long, very long, let's say infinite wire. And then basically what's going to happen is that, somewhere here I basically stuck a one end of a capacitor here and the other end of a capacitor there, okay? But this thing is hooked up to a battery, so as we know, even in circuits that have capacitors, currents can flow, right? And so what happens is that there is a current that's flowing along this wire. It does not. There are not electrons that are flowing through free space in the capacitor. But what happens is that there is a current here, and when those moving charges reach this plate, they basically start to accumulate onto the plate, okay? So it's like, you imagine there's a flow of traffic on a street, these are cars, and basically there's some very large reservoir where you can store cars, like a big parking structure. And basically as you are flowing a current of cars into your capacitor plate, it's like, they're just starting to occupy the parking structure until it gets full and then the current stops. But let's say now that parking structure is still partially open, so we can have a finite current that's flowing into it. And likewise here, we have negative charges accumulated on this plate. We have a current flowing this way, and it's like the cars are exiting the parking structure on this end, right? So there's like two different parking structures. You can think of the capacitor plates like this. All right. So because we have a positive charge on this plate and a negative charge on this plate, that will generate some electric field between the plates, right? We learned earlier on when we dealt with capacitors what the electric fields were. They were quite easy to calculate for a parallel plate capacitor. We'll use that result in a second. So there's some E field here. All right. And let's imagine now we wanted to calculate, let's say, a magnetic field. Okay, so let's say I'll take some point over here. And I want to see if there is a magnetic field. Well, there is a wire. There's a long wire here and a long wire here, and they're both carrying a current. So, you would well expect that there should be a magnetic field generated by this wire that is indeed carrying a current through it, right? And if you, use the Biot-Savart law and you just calculated, basically this segment of wire and that segment of wire, what the magnetic field would be at P, you would indeed get a finite magnetic field. Okay, so there should be a magnetic field at point P because it's very close to a current carrying wire. All right, so let's imagine now that we have let's try to calculate what that magnetic field would be by using Ampere's law. Okay, so let's imagine I pick an Amperian loop like this. So some circle, that is coaxial with this wire that encloses P. All right, and so we know that basically B dot dl, the integral around this loop of the magnetic field, is going to be equal to mu naught I enclosed by basically this Amperian loop, or the surface that basically you can associate with this loop. But actually, it turns out you can generate any kind of surface as long as this is kind of like the perimeter, right, of that surface. You can pick sort of any surface you want. So one such surface might be something as follows. It might be something, use yellow. So it could be something like, this may not come out so well on your printout, but so I'll call this surface 1. Right, so it would just be, a flat surface, exactly in the plane of the loop. All right, so that's a perfectly fine surface. But in fact, I could actually pick another surface. I could pick one that looks like this, right? So imagine this is the open surface, and I basically had something look like this. So it looked kind of like a squared off bowl or something, okay? So, or like a pot. So let's say it basically extended a little bit past this plate, right? So basically what it looked like was, this was open. This is like, the top of our pot. This is like the base of our pot. So this is our closed surface here, right? And then these are the sides of the pot. All right. So I'll call that blue one surface 2. So that's this one here. And the yellow one is just that surface. Okay. So they basically incorporate the same Amperian loop, which is this blue one. Both 1 and 2 have the same Amperian loop. All right. So if we consider surface 1, right, we have B dot dl for this dash circle here is going to be equal to mu naught I enclosed The amount of I enclosed is just, I'll call this I sub W. That was the current in the I, W is for wire, so it's current through the wire. So it's mu naught IW. Okay, well, let's look at surface 2. So B dot DL, it's going to be the exact same loop that we would calculate for number 1. It's still this guy here. But now how much charge does this, how much current is basically punching through this surface, right? I've drawn this kind of funky, bowl-shaped surface here. And actually, because the sort of the flat base, the solid surface is over here, you can see there's actually, and this is supposed to be a little bit past the end of this capacitor, there is no current flowing through it, right? There's a current kind of flowing into the bowl, but nothing ever sort of punches out that surface. Because basically this bowl is sort of, containing, it's sort of holding this capacitor plate in it. So no current is exiting surface 2. So mu naught I enclosed would be 0. Okay? So no current even though no current flows through surface 2, even though they basically, utilize the same Amperian loop, both 1 and 2. All right? So this clearly is bad, right? We have something, so basically the left sides of the equation must be the same because they use the same Amperian loop, but the right sides of the equation are obviously different, right? So how to reconcile this is our question, all right? Now, just, this equation 2 would suggest that probably there is would be no magnetic field around this loop. And we simply know that's not the case, right? I mean, if we just used the Biot-Savart law and just did a direct integration, we have a current flowing through this wire, a current flowing through that wire, and you can easily convince yourself there should be a finite magnetic field here. So something has got to be amiss. And so basically, I'm going to describe this. This is where we're going to talk about this quantity called the displacement current. So let's look at it like this. Now, we do have a current. If we have a current, let's say if this is not obviously a completely continuous infinite wire, right? There's a break in this wire, but we do have a current flowing. And so what's happening is that current is moving charge, and if this wire has a break in it, then if this current is carrying charge, then charge must be accumulating somewhere, right? So on these capacitor plates, for instance. So obviously, basically, charge is conserved. So the charge that's flowing down the wire has to go somewhere. It's dumped on these plates. It's accumulating. If the charge is then accumulating on these plates, that means that there has to be an electric field between these plates. And if this charge is changing as a function of time, that also implies that this electric field between the plates must also be changing as a function of time. All right. Another way to look at this, if you didn't like this sort of analogy of these two bowls, 1 and 2, I could define another point. Let's take a point that's sort of right in between our two plates. Okay, so let's imagine we're at the midpoint of the plates, and I'm going to try to figure out the magnetic field here, right? So, if you use the Biot-Savart law, I have sort of a half infinite wire here, a half infinite wire there. They're both carrying current that way. So basically, by using the right-hand rule in the Biot-Savart law, I should find that there's a magnetic field sort of pointing out of the screen, right? But if I define an Amperian loop like this, right? Again, this loop would not enclose any physical current through it, right? So yet, even though I kind of suspect that there really should be a magnetic field here, if I chose this Amperian loop, what I would find is that, I enclosed would be 0, So, what gives with that, right? So Ampere's law is clearly not consistent with sort of our intuition or what we would get by calculate using the Biot-Savart law. So it's basically the same kind of argument I made here with these two surfaces. All right, so the question is, how do we address this inconsistency? We're basically getting two different results depending on what kind of closed surface or what surface we associate with our Amperian loop. So what this kind of suggests is that we're missing a term in Ampere's law, and this gets back to when I was talking about Maxwell's equation. This is Ampere's law here, and I argued, well, we have this sort of time-varying magnetic flux term associated with this E dot dl, so maybe there's a time-varying electric flux term that's associated with B dot dl. So let's just start by thinking about this electric field that is set up between these two capacitors, right? So we know that the electric field between the capacitors, the magnitude, like we know it's, in this case, going to be to the right. Right? We learned that it was sigma over epsilon naught, where sigma, this was from earlier on in the semester. Sigma is the surface charge density on the plate. So it's the charge per unit area. We're assuming there's a plus Q here and a minus Q there. So it's just going to be Q A, right? Q over A is sigma epsilon naught. So that is my electric field from this capacitor. And, as I argued, if we have a wire that's carrying current, but there's a break in it, then that current must be dumping charge somewhere. So there must be some charge, some amount of charge that's changing on these plates, which must result in a time-varying electric field in the gap region, right, between these plates. So let's think about what the rate of change of the electric field is, right? So I can take the time derivative of this electric field. That gives me the rate of change of that electric field. All right, so it's just d by dt of Q over A epsilon naught, right? That's just this term over here. Well, A and epsilon naught, the capacitor plates aren't changing in size. Epsilon naught's not changing in time. So really what this is just 1 over A epsilon naught times dq dt. Right? So what is dq dt? dq dt is basically the rate of change, basically the rate at which charge is being increased on this plate, right? So if I think about this in this way, again, if I think of this as being a road with cars driving down it, which define the current, and then the amount of cars in the parking structure as being the charge, then basically, the rate at which cars are entering the parking structure is going to be the rate at which the number of cars in the parking structure is increasing. So basically, this should just be I sub W. Okay, I hope that analogy made sense. I can just take this, right? So I have I sub W. That was this fellow here. I'm just going to rewrite this thing. I'm going to move the 1 over A epsilon naught over here. So I'll multiply both sides of this equation by A epsilon naught. So I get an A epsilon naught dE. This is electric field through the capacitor dt. The A is just a constant. It has no time dependence. So I could write this as epsilon naught d by dt of A times E through the capacitor, right? Because I can pull this in, I can pull A in and out because it's just effectively just a numerical factor, if you will. So this is just my electric flux, right? It's basically it's the integral of the electric field over the entire area of the plate. Since the electric field is constant over the plate, we're just going to say that it's, we can just say it's E times the area of the plate. So this is my phi sub E. So I can write this then as epsilon naught d phi sub E dt And this I am going to call my displacement current. I sub d. So this is our missing term in Ampere's law. Okay, so if we basically now can write down sort of a generalized Ampere's law, it's going to have sort of the normal term. Well, it'll just be B dot dl as usual on the left. Then I'll have the sort of the normal current term, mu naught I enclosed. This is sort of a real current, plus a mu naught I displacement current term. Okay, where I sub d is this quantity here, and I'll argue in a second why we can really think of that as being the case. So in other words, I can just write this as B dot dl mu naught I enclosed plus mu naught epsilon naught d phi e dt. Okay. So this is sort of our new and improved Ampere's law. So actually what this should have had here is that it's actually a plus, and there's an epsilon naught. So I'll just erase the minus sign so I can squeeze that epsilon naught in there, okay? Or, whoops, mu naught. Epsilon naught. Hard to read, okay? But you can read it, see it down here. So this is the generalized Ampere's law. So, let's think about what this means. So let's imagine we have, example. Let's imagine we have basically effectively an infinite wire. And we have a very teeny break in it. So something like this, right? So we have some current that is flowing through the wire. And there's a capacitor somewhere in the middle, okay? But you can imagine if we are very, very, very far away from, this wire, let's imagine you can't even see that capacitor there. There's this sort of, little tiny capacitor there, but we're so far away you don't even notice it's there. So for all intents and purposes, it just looks like an infinite wire. And let's say I was sitting some point P, just directly in the middle of this, directly above this capacitor, okay? So if I wanted now to define an Amperian loop, so just, before we even try to do any calculations, if this was, I'll call this I naught, or IW, I'll call it IW again. There's IW through the wire. So we know that basically the field at P should basically be approximately that from an infinite wire, right? Because this little break here is going to be so small, we're not even going to notice it. We just basically see this big long wire with a current flowing through it. It's going to be an infinite wire. So basically it should just be, what it is for a wire. It'd be mu naught I in the wire over 2 pi r, where r is the distance, it's the radial distance from the axis of the wire to point B. All right, but we just said that this thing was directly sort of in the middle of where the wire is. So, I'm going to draw some Amperian loop. And this is a perfect side view. Little circles again. So this is going to be a perfect side view, but, it is going to be a circle. but we're looking at exactly edge on. Okay, so again, for this circle, no physical current is passing through that loop, right? There is a loop there. I mean, I've drawn it side on, but just, trust me. So there's no physical current passing through it, but we know that basically the current should basically be something like that. We actually calculated earlier that I sub w, right, is equal to epsilon naught d phi e dt. That's the flux, through that loop here. So basically, you can kind of imagine that this should basically be equal to mu naught over 2 pi r, and replace I sub w by basically I sub d, which is this guy here. Because we're basically saying this displacement current is equal to the actual current in the wire, and we know that basically, even though there is no current actually passing through this Amperian loop, it's going to have a magnetic field pretty much exactly like that of an infinite wire, right? It's going to be 2 pi r here, and I'm going to substitute this expression here. So it'll be epsilon naught d phi e dt, right? So hopefully I've sort of convinced you that even though there is no actual real current flowing through this wire, when you're really far away, you don't even notice there's a break there. So this thing's got to behave pretty much like an infinite wire. So then, basically, since we've said here that the displacement current through that capacitor, the displacement current, total displacement current through these capacitor plates is basically equal in magnitude to the current flowing through the wire, kind of makes sense that basically we can just replace I sub w with I sub d. So this has something to do with the time varying field through the capacitor. And so, when the capacitor is entirely charged up, so, I sub d will go to 0 when there is no time varying flux. So basically, when the electric field here stops changing, right, what that means then is that basically the current, the rate of change of the charge on the plates is no longer changing, which means basically the current is going to 0 as well, right? So basically, when we've sort of completely charged the capacitor up, basically that parking lot is full. So basically now, there's effectively a traffic jam here. No more cars can enter the capacitor. So I sub w is 0. But on the other hand, the electric field between the plates is no longer going to be changing in time because we have no more, there's the rate of change of charges accumulating on these plates becomes 0. What I want to do now is change gears a little bit. So basically this is now just as a recap, this is our basically correction term to Ampere's law. So basically, in addition to an electric field, a current flowing through an Amperian loop generating a magnetic field, in addition, a time-varying electric field can also generate a magnetic field as well. And this is not just a curiosity. It turns out, again, for our theory of light to be complete, so basically that Maxwell's equations, in fact, define our theory of light propagation, we need actually to have these time-varying terms here. So they're not just sort of, curiosities. They actually are very, very important to the way our universe works. Okay, so now I want to change gears a little bit and talk about inductance. Okay, so let's imagine we have two coils, okay? So we have, or maybe, there are actually a number of coils here. So we have sort of one set of coils with, this first one in red. We'll say there are N1 coils here. It could be 10. And then, very close to it, there's another set of coils. Maybe there are 5 coils here, but we'll call that N2. And so what will happen, right? So if we have then, if we apply a current to N1, right, there'll be some magnetic field that's generated by N1, and that will also go through N2. So basically, if I generate a magnetic field from N1 due to, let's say, passing a current I1 through this set of coils, right, there will be a magnetic flux through the green set of coils, right? And so if I1 is varying in time, so let's imagine, there was no initial current, and then I just, closed a switch, there was a current that turned on, so basically now I started ramping up a magnetic field, there would be a magnetic flux through these coils that would be time varying, right? So if I change I1 with time, the magnetic field here changes with time, so the magnetic flux through these coils also change with time. And we know from Ampere's law from Faraday's law, that basically a time-varying magnetic flux gives rise to an EMF in the loop. Okay? All right, so if I write down using Faraday's law, so let's assume that there is let's write this out here. All right, so if there is a time-varying current I1 through the left set of coils, that generates a time-varying magnetic B field, drawn here in blue, and basically that will generate a time-varying then magnetic flux through the right side of coils, right? So if I'm going to write down Faraday's law, this is the induced EMF in the right side, the green set of coils. And that's going to be equal to the total magnetic flux, the time derivative minus the time derivative of the total magnetic flux through these coils. So what I'm going to do is I'm going to say that there's a minus sign. Let's imagine there are N2 coils. Maybe there are, N2 might be 8 or 5 or whatever, these coils. And what I'll write phi 2 is, that's basically the magnetic flux through basically one coil, right? If I only had one coil here, I would draw this one surface. Since I have like 8 of these coils, and let's imagine they're not very far apart, they're just stacked very close together, kind of like a solenoid that's very tightly wound, then the total magnetic flux, it would be basically going through 8 sets of coils. I have to multiply by the number of coils that I have. And I'll assume the amount of flux through each one of these coils is the same because they're very tightly wound together. In the end, I actually don't need to make that assumption, but for these purposes, it's kind of useful. All right, so basically then, right, so it's going to be equal to minus N2. Now, the flux through the set of coils here, right, is going to be proportional to, proportional to the magnetic field that's generated by N1, right? So, for instance, if these were 2 solenoids that were very close together, right, then basically, phi 2 will depend on the strength, depend on B1 generated by this set of coils. So, if it was an infinite solenoid, right, it would be something like mu naught N1 over the length of this, if it was a kind of quasi-infinite solenoid, it'd be like this times I1, right? If it was a ring, if N1, if the red or the left set of coils was just a single ring, we know that goes as basically mu naught I1 over 2R. So the main thing, and then, if these coils were a little bit further apart, not all the field lines leaving the left coil would go into the right one, so maybe it would only be like factor of 2, it would depend on the area. So there's a bunch of factors into calculating what phi sub 2 is, right? How close these coils are, the radii, relative radii of the coils, whether or not this is a solenoid or a ring. There's a bunch of factors in here, but the key thing to take in mind is that phi 2 will be proportional to B1, right? Phi 2 will be proportional, that's our proportional symbol, to the magnetic field generated by this left solenoid. And we know in all of our equations for, whether it's a solenoid or a ring or a wire, the magnetic field is always going to be directly proportional to the current, right? If I double the current in this ring, the field will double. Or if I doubled the field in a solenoid, the field would double. If I doubled the current in a wire, the field would double. Okay, so basically the field is always proportional to the current. So we can see here that the flux through this right set of rings is going to be directly proportional to the current flowing in the left set of rings, in the red set of rings. Again, so let me just say that again. The flux through the green set of rings is always going to be directly proportional to the current flowing into the left set of rings or wires, right? So basically, if I double I1, I would double the flux through here. No matter whether or not these things were separated a little bit further apart, if one was a solenoid, one was a ring, it doesn't matter, okay? So in that case, then, I can write E sub 2 is equal to minus N sub 2, right? And so what I can then do is I'll just say that I know that phi sub 2 is going to be directly proportional to I sub 1. So I'll just say phi sub 2 is equal to some unknown constant times I1. Okay, so this is some proportionality constant. So if there were two solenoids very close together, it might be, there would be a mu naughts, N1 over L, there would be N2 in there, and all these things, or N2 is actually included in here, but it doesn't really matter what the geometry is. So I basically just say, okay, there's some constant C. So this is all right, so as I just wrote here, so C is just some proportionality constant which depends on the geometry, how far these are apart, whether these are rings or solenoids, or, et cetera, right? So I'm just going to rewrite this. E sub, the EMF induced in this right set of rings is minus N2 times d phi 2 dt. That was just what we said before. So it's minus N2. I'm going to basically say phi 2 is equal to C, so this proportionality constant times I1. So basically it's going to be d by dt C times I, right? And since C is basically some thing that depends on the geometry and the separation, that is not varying in time, right? This is just some geometric factor, so basically it can be factored out here. So basically, again, I'm going to just cancel out these minus signs. So I get N2 d phi 2 dt is equal to N2 times C, this proportionality constant, d, this was I1, di1 dt, right? Since these are both time derivatives, I can sort of cancel out my d by dt's, or I can just integrate, if you will. So then what I get is that basically N2 times phi 2 is going to be equal to this thing, that's a constant. I'll call that M21. All right, so basically M21 is what we call the mutual inductance of this configuration. And so I can write M21 as equal to N2 phi 2, which would be the flux that this first left set of rings generates on sort of one of the rings on the right. And then I multiply that by the number of rings to get the, sort of the total flux through that whole setup on the right over I1. So I can actually then run this argument in reverse and say, well, if I generate, instead of pumping a current through, the red set of coils and looking at the voltage generated on the right side of coils, the right set of coils, that's basically what this M term is telling us, is basically if I generate, a time varying current here, how strong of a voltage, is generated by this, picked up by this set of coils. I could do this in reverse, right? I could basically now send a current through this set of coils, that would generate a time varying magnetic field going the opposite way. And then we could see how much, EMF is picked up in the left set of coils, right? So I could do this sort of exact reverse argument. I won't kind of go through the long, laborious recalculation of this. But what I basically want to say is that it turns out that when you do this calculation in reverse, you use the exact same proportionality constant C, which you can kind of imagine, right? If basically, C has something to do with, the separation. So these are far apart. If I generate a field here, less of that field will be picked up by this loop. But certainly what that means is if they're far apart, if I generate a field on this guy here on the right, less field will be picked up on the left loop, right? So certainly it's not hard to imagine that this proportionality C sort of works both ways. It would be the same C you would use, for this one generating a field into that one, or vice versa. So turns out that basically I can write M12, which is basically the opposite situation, which is basically I pump a current through the right set of coils and I look at the EMF picked up by the left set of coils. And so M12, right, is going to be equal to N sub 1 phi sub 1 over I2. It's sort of the exact reverse. And these two are actually going to be identical to one another, right? And the reason is basically, as I said earlier, it's because this proportionality constant C is sort of the same regardless of whether or not you pump a current through the left coil and measure the EMF on the right, or pump a current through the right and measure the EMF on the left, right? If I move them further away, obviously the effect will go down, in either way. If I double the number of coils on one, then this one will pick up more EMF, or vice versa, it would generate more EMF for this guy to detect. Then if I, again, this quantity here, look at this quantity here, this was E2. So what the mutual inductance tells us is basically, E2 is going to be equal to, or actually if I go back here, there was a minus sign because N2 times C is basic, our proportional constant was M21. So basically E2, and I'll just call this M, because M21 and M12 is the same. So basically E2 is going to be minus M di1 dt, and likewise E1 is equal to minus M di2 dt. Just written here, the mutual inductance can really be defined as the proportionality constant if I basically am changing the current, the rate of change of the current in one coil will induce an EMF in the other coil. And basically the mutual inductance is the proportionality constant between, the time rate of change of this current to the voltage picked up by that loop. And it's the same quantity regardless of whether or not I, have a time varying current in loop 1 and pick up a voltage in loop 2, or if I had a time varying current in loop 2 and I measured the voltage in loop 1, that proportionality constant is the same either way you slice it. And again, you can basically calculate like this. So if you basically said, I have, some number of loops here, I can calculate, if I calculate the magnetic field generated by this loop here, and I calculate the flux, through, let's say, one of these loops here, that's phi 2, and I divide this by the current, right? Because we always know that that magnetic field that's generated by this loop will always be proportional to that current. So dividing by I1 or I2 takes that proportionality constant away. So in the end, basically, at the end of the day, inductance is just an effect where, it's basically just a sort of a byproduct of Faraday's law. So if I have sort of two, coils or loops close to one another, if I have a time varying current through one, that basically will generate a changing magnetic field in the other. That will result in a changing magnetic flux through that next set of coils. And that, as we know from Faraday's law, generates a time varying electromotive force, right? And so this is actually a very important effect, as we'll basically explore a little more in the next lecture. This basically our entire power grid depends on this sort of effect for basically, for what we call transformers, so stepping up and stepping down voltages. We'll talk a little bit more about that next time. So sorry that this lecture went on a little bit longer than usual. We had to sort of introduce a couple different topics, both the displacement currents, right, that we talked about over here, and also the inductance that we introduced as well. Okay, that's it for today.